Hello. So today we're going to talk about the second law of thermodynamics, and this should just about wrap up our first unit. So we are nearing the end here. We've already discussed the first law of thermodynamics, a lot of different heat transfer situations and how work can be transferred as well. In the first law of the first law of thermodynamics specifically was talking about how overall you don't have a net change in your internal energy. So your work lost and gained will be balanced by the energy lost and gained. So the second law of thermodynamics is almost like an amendment to the first law. It talks about how that's not always the case and how it is impossible to completely conserve the energy that is being moved around within these systems. So today, we're going to focus on recognizing why the second law of thermodynamics requires two bodies at different temperatures for work to be done. We will calculate the efficiency of a heat engine, and we will relate the disorder of a system to its ability to do work or transfer heat as energy as heat. So with the efficiency of heat engines, we're going to get this new formula here. It's not really a formula, it's more of a relationship, okay? So we already knew this, that the net transfer of heat is going to be equal to the difference between the hot heat area and the cold heat area. And that is also equal to the net work. So the formula for work done by each cycle of a heat engine derived from the first law of thermodynamics is going to suggest that all work is conserved in a cycle, and then more work is gained by taking more energy at a higher temperature and giving up less energy at a lower temperature. The second law of thermodynamics states that no cyclic process can convert heat entirely into work. So it's impossible to construct a heat engine that absorbs energy from the heat source and then does an equal amount of work. You're always losing a little bit of heat somewhere. So in this picture, this shows a heat engine where you have an area of high temperature. So let's say we are talking about water being transferred here. So you have an area of a high heat, so that the hot water comes into the system. That heat energy can then be transferred out as work, mechanical work, but you're also losing some of that heat to the low temperature area. So you have hot water coming in. Some of that heat's going to be given off into the cold, the dump into the cold area, and then you will also gain some work, or work is being done, I should say, onto your surrounding environment. Okay, so the heat comes in, some of that goes out to be work, but you're also losing some of that. So a really good example of that would be a coal power plant. So I'm sure most of you are familiar. There's coal power plants here and there. And if you notice, most of them are right along a large body of water or a river. So if you think about the one in Portage-de-Sioux over in St. Charles County, it is located right on the river. And that's because they are using the river as their cool water source for their heat engine. So a heat engine is required to give up some energy at a lower temperature in order to do work. So it has to cycle through the cool condensing area in order for work to be done. The heat transfer can never be equal to work in a cyclic process. So some energy must also always be transferred as heat into the environment, so that your transfer of heat out of the environment has to always be greater than zero. Okay, so in this case, you have a picture. This diagram here is of a heat engine on a pretty large scale. So this would be a coal power plant. Okay, so you have the river over on the left-hand side. You have the large pile of coal, and they're funneling the coal into the stack, right? So the coal comes into the boiler, and it's the furnace basically. So you are burning the coal. That energy is being transferred into the water pipes, and then the water is being pushed throughout the system to convert that into mechanical energy. So if you look at this, your exhaust energy from the power plant has to be removed as heat to a lower temperature substance such as water. And the river provides a continuously flowing area of fresh, cool water. So we have the coal coming in, it's being burned, transferring its heat here. you are going to produce steam with the water, obviously, because the water is heating up, it's creating steam. We know that steam has a lot of kinetic energy. Steam is going to come down into, it's going to be forced down into this area with the turbine, and the energy from that steam is going to be transferred into the energy of the turbine. Is going to cause the turbine to move, I should say, which is then transferred into work and mechanical energy. So once we get that transferred into work, we can then convert that into electrical energy and send it on out. So that part of it is kind of taken care of over here. But on this side, you still have this water system. Okay, so the steam is going to come in through here. It's going to transfer its energy to the turbine, and then the steam will cool off. Okay, so it's going to cool off and condense down into this part. So now you have this hot water here. You still have the steam coming in, and this water needs to come out into the cool area in order to do work. Okay, so this is the heat engine part. So you have the heat coming in, the work is being done, and then it has to cool off. Okay, so that is our heat engine. So in order for work to be done here, you have to be able to transfer some of that heat energy back out. So you have heat coming in, heat going out, and then work is being done. Kind of a interesting fact while we have this topic up, most smokestacks are going to be 500 to 900 feet tall. And there's a reason for that. It's because of where they land in the atmosphere, where they push out their pollution in the atmosphere. So if you get smokestacks that are higher than the inversion layer, then you will keep that pollution up above you keep it up above basically where the drafts won't pull it down into the environment that we live in, but it'll keep it up higher in the atmosphere. So if you have different heights of smokestacks, if they're lower, different temperatures can cause that pollution to come down, kind of just based on the draft of the wind and the temperature. So you can get different patterns of pollution spreading. I just thought it was interesting to kind of show you, and the way that the temperature can affect the plume shape and the height and the inversion layer. Okay, so here's some other examples here. So the idea is to get it up above the troposphere, because that's where we are at, right? So if you keep it up higher than that, hopefully the idea is that the temperature will be suitable and the wind conditions will be suitable to keep that pollution up high. It's not perfect, but it is better than nothing. So here's more examples of that. So as the temperature decreases here, the altitude of the smokestacks can be lower. So if you're in an area where it is very cold, then you can have lower smokestacks. So if you have an area where in here is, here's an example of the warmer temperature. Okay, so kind of zigzags here. We have the warm air coming in. So if you end up with a warm layer, then it's going to trap your pollution down here. So if your warm air is able to escape and go upward, then you will get rid of that pollution more quickly. But if not, then it's kind of stuck here under this warm layer. So kind of back to heat engines, we were talking about the way that cycles through. Okay, so if we have this, you know that we are doing work here, the hot comes in, it does work, the cool goes back out, or it transfers the heat into the cool, the sink, basically, which is the river in that case. So the second law of thermodynamics tells us that no cyclic processes are 100% efficient, but we know that some are more efficient than others. So efficiency is to be a measure of the useful energy taken out of a process relative to the total energy that's put into the process. So that's where you get this ratio of work being done on a system down at the bottom here. So the efficiency of a heat engine or any cyclical system will be the ratio between the work done and the heat put into the system. Okay, so typical efficiencies for heat engines, you have couple different types of engines here. Steam engines are going to be not very efficient. Okay, it's part of the reason why we don't really use them anymore. The most efficient type of engines are going to be gas engines, because they're able to harvest more of that work through the heat that's being transferred. So here's an example. So if we want to find the efficiency of a diesel engine that during one cycle receives 462 joules of energy from combustion and loses 254 joules as heat to the exhaust. So we know that the heat being put into the system, so the QH, is 462 joules, and then the heat being lost from the system is 254 joules. So how efficient is that? So your efficiency in this case, since we don't have the work, we're going to use, we're going to have the heat lost divided by the heat gained, and all of that is subtracted from 1. So the efficiency of this heat engine, or this diesel engine, I should say, is going to be 0.450. So only 45% of the energy added as heat is used by the engine to do work. So as expected, the efficiency is less than 100%. Another example here, so suppose the first steam engine's efficiency was 8%. How much energy must be transferred by heat to the engine surrounding if 2.5 kilojoules is transferred by heat into the engine? How much work is done? So we have two questions here. We're trying to find QH, so we're trying to find the heat transferred into the engine, and then also how much work is done. I'm sorry, not QH, QC. So we know that we have heat being transferred in. We need to know how much energy must be transferred in order for that to happen. So we're going to find the efficiency of this engine. So we know that the efficiency is 8%. We're going to write that as a decimal, set equal to 1 minus the heat being lost divided by the heat that was added in. So in this case, we get the heat being lost as 2,300 joules. Then we can then substitute that into our other form of the efficiency formula to solve for the net work done. So you have your efficiency is 8% set equal to net work divided by the heat that's transferred, the heat's transferred into the engine to give you the net work of 200 joules. Entropy is going to be the very last thing that we talk about. And entropy is kind of interesting in that there's a lot of ways to describe it, but it's more of a statistical situation. So entropy is going to be the measure of disorder in a system. Okay, so in thermodynamics, we know that systems tend to go from a state of order to disorder. So if you are increasing the pressure in a system, think about the molecules. You increase the pressure of a system, those molecules move faster. You change the temperature, you are moving the energy from one place to the next. So you make any changes at all in a thermodynamic system, you are increasing the disorder in that system. So entropy of a system tends to increase overall. So you are going to use this formula here for the change in entropy. Okay, so entropy is represented by the variable S, capital S. So we know that change is your delta. So we have the change in entropy is equal to the heat added or removed divided by the temperature of the system. Okay, so you typically go from a highly ordered system. You start changing things about that, different physical characteristics. You're going to get more and more disorder. So heat engines are typically limited because only some of the energy added as heat can be used to do work. So it's partially because molecules do not move in an orderly fashion, which makes less efficient energy transfers during collisions. Okay, so that's part of the reason why you're losing some of that efficiency there, because you cannot control the way that molecules will move. So if you are counting on them colliding with one another to cause pressure or different energy, kinetic energy increases, you can't count on that because the molecules are going to just be moving in many different directions. So anytime you are adding energy to a system, you are increasing your entropy. So that is your main focus for today. So please look at the assignment and let me know if you have any questions, and I will talk to you guys next time. Also would be important at this point to get in contact with me if you do have any questions, because we will be looking at studying and reviewing for the exam pretty soon here.